So thank you for the introduction. Thank you for inviting me. So yeah, I recently moved to France to Grenada, but the work I will be presenting you is a work that has been done in Japan while I was there, and is still being done actually in the Joint Robotic Laboratory, so Geneva. So this is a work about manipulating large, long objects, deformable objects. So this is a work that is mostly done by Lee Quinn, which is one of my PhD students, and I will also show some results from Kevin Shapley, who was also at the. So to give you a bit of context, there is quite a few industries where you have a large bobbin with deformable material rolled on it. For example, this material can be paper, fabric, rubber, cable, and so on. And there is the need for workers in these factories for this kind of industry to manipulate both the bobbin with the material and the material to put it in another machine or such kind of information. And so we were contacted by an industrial partner who proposed us this.
Limited.
Who proposed us this kind of scenario. So we have a bobbin, which is a large bobbin. It's more than 1 meter diameter. It's more than 100 kilograms. That starts from a point. You know the environment. You want to bring it into an unwinder, which is a part of a bigger machine that will take the material and use it for further process. So in the lab, we have a replica, or at least a good enough replica of such kind of unwinder. What the partner asks us is, can you do that? So bring the bobbin into the unwinder and then set up the belt, as you can see on the right image, with a humanoid robot. So I will be mostly speaking about this part, which concerns more the deformable object part, but I will just introduce it the rest. So this is my plan. So I will go quickly on the bobbin manipulation and then mostly about the belt setup. So here is a demonstration we made in the lab, so this is the part about bringing the bobbin to the unwinder, and it's an opportunity for me to introduce several of the tools that we are using also in the manipulation part. So this is the HRP5 robots. Here you have two views superimposed that are on the top a slam view, and on the bottom it's a depth view of the robot. So in the tools that we are using to be able to achieve this demo completely autonomously, we have done slam, where the map has been done before because we know the environment, so the robot is reusing the map that it has. We have a local manipulation planner. So the point is, okay, how do I plan for the motion of the bobbin? But knowing that you have a robot that needs to manipulate the bobbin, and you need also to plan for the footsteps of the robot and to take into account the kinematic limits and the dynamic limits of the robot. So this is the local manipulation part. There is, but this is not something that I will be using later, so bobbin registration. So from the depth field of the bobbin, which is a large, used with a large angle camera, we can detect what is the position of the bobbin, what is the orientation of the bobbin, and use that to know where to grasp the bobbin with the robot, and also be able to mask out the bobbin from the slam part. And all of this gives inputs to a QP-based control, so whole body controller. So you have a number of tasks which are grasp the bobbin, remove your arm, move your foot, and so on, keep stable. So all these tasks are linearized and put either as constraints or as objective in the QP-based optimization. And the result of the optimization is sent back to the robot to be executed. All of this is supported by frameworks that has been developed in the lab. That is MCRTC framework, which is really all the machinery around QP-based whole body control. So thanks to this, all of this machinery, all of these elements, we are able to have this millimetric precision on this big object. Sorry, not millimetric, centimetric precision on these big objects, and able to glue them where we need to. Okay, because we have not so much time on just. So then, when it comes to now manipulating the belt, so what I call the belt is one way we design this band that we have, which is a kind of rubber band that we have in the rim. So the first thing is that in some cases we know that we will need to detect the shape of the belt so that we can be able to manipulate it. And so the vision part we have is a RGBD camera, from which we can get a point cloud. So we do some downsampling and color segmentation to isolate the belt. So one of the things that there is no pattern at all on the belt, so we really need to get the information from depth and color. And from this point cloud, we want to reconstruct the shape of the belt. So we have been using the current point drift algorithm. So the idea is that you have a kind of mesh model of the belt, and you will get a probabilistic representation of it, and ask the question for point cloud and the deformation of this model. What is the probability that this point cloud is sampled from this model? So the current point drift was, we discovered it at least for 1D shape, and we applied it to 2D shape. And the idea is really to optimize the shape of the model, so that we maximize the probability that the point cloud is taken out from the model. A nice feature of this algorithm is that it's reasonably robust to partial occlusion. And since we are manipulating an object and we will have the hand or the arm of the robot in front of the object from time to time, the vision being in the head of the robot, we need to be able to be robust to partial occlusion. So this is one of the examples where we use it. So the robot does not have the finger capabilities to grasp the belt directly from the bobbin. So here, in an example we did for iOS 2020, we are applying a compliant motion on to scrape out the belt from the bobbin. Then the robot is able to detect the shape of the belt and to know where to put his hand to grasp it. So then the main part of this work is the manipulation part, the planning part, sorry. The planning, so we have several steps sequentially. So the first one is to pass for the ideal pass of, plan for the ideal pass of the belt, then pass for the gripper of the robot, and then go to the footsteps to follow what we want the gripper to. And then we can send all of that to the control and use the tools that I showed you before, so the robotic control and the SLAM, to be able to execute in a precise manner the planning. So the first thing, quickly going over, is the footstep plan. So we are reusing the local manipulation planning I was talking about before. The idea is that, okay, from the pass of one gripper or another gripper, we want to find the footstep plan that is able to support this pass with the robot keeping being stable. So for that, we need to build a reachability map. In our case, we want the reachability map to be just in a plane in front of the robot, but with the orientation of the gripper taken into account. And then from this reachability map and the local manipulation planner, we can get the footsteps that goes with the motion movement. Then for the planning of the manipulation in itself, we are making a kind of bold hypothesis. Our claim is that we don't need to simulate the deformable object. We don't need to simulate the belt. The idea being that planning with a high dimension object is always more difficult and longer to do. So we wanted to try to see how far we can go without simulating the belt. And the idea being that we could be able, with some assumption, to find back the configuration of the belt from only the configuration of the grasp point and the path we had so far. So we are making two assumptions. One is that the belt is sufficiently stretched. It means that, in this case, it means that between all the axes on which you are going, there will be a straight line, and between the last axis of cylinder and the grasp points, there will be also a straight line or almost straight line. The second assumption is that when we are grasping the belt, not at the end, we are grasping it close enough from the end so that the remainder of the belt is straight. It's not deforming too much, which we can suppose because we have something that is not too deformable. So to enforce the second assumption, we did some tests directly on the robots. So here, this are tests with an old gripper that we change a bit the shape of the fingers to have a bit better results. But you can see that, for example, when we grasp at 20 centimeters, and depending on the orientation, the belt remains straight enough for our purpose. So we encode that in the confidence area model, which is okay depending on the angle at which the gripper is grasping the belt, how long can the belt remain stable? How much of the length of the belt can remain not stable, so not straight. Then we can make some several simplification on the problem due to the nature of the belt. So one of the first things that the belt will not twitch; it will stay in the same plane all the time. So it can be considered as a cable in 2D. We don't need for the belt part. We don't need the 3D information or the depth information. Then, for the purpose of planning, we just consider that the gripper can be a cylinder, and so we need to be careful about the orientation after. But in the first approximation, it's okay. And we divide the space in which we want to plan in the depth part into three areas. One area where there is only the belt, and so there will be obstacles that are obstacles that we call T1 type 1 obstacles that are obstacles for the belt and the gripper. One area that will not be concerned with the belt, which is the front area where there is only so the obstacles here will be only obstacles for the gripper, and then one area where the gripper can move free. So then it becomes a matter of finding a path that is okay for the belt only in this area, that is okay for the belt and the gripper in both areas, and so we call that 2.5. So the planning in itself is done in several steps. So as I said, first we want to find the plan for the belt in itself. So the input of the planning is as such. So we have the cylinders along which to rotate with the orientation we want. We have the possible obstacles that are in the plane of the belt, and we have the start point and the end point, which is the start. So the very first thing is to compute the nominal path for the belt, so which is the path that you should have at the end if everything goes well. So for that, we rely on a paper from Jiangsu 2019. Then this gives us the homotopy class of the shape of the path for the belt, and we need to encode this homotopy class in some way. So we are using a work from data sharing here. The idea is that you can, from each obstacle in this plane, you can draw a line with a minus and a plus. And the homotopy class can be specified as when your path is crossing one line and from which side it's crossing the line. So for example, here we are not crossing the line for A1 or T1, O1. We are crossing the line for A2, so the first index from this homotopy class will be A2 minus. And then we are not crossing these lines, we are crossing the lines for A4, so we will have A4 minus. If we are looking at this path, here we will cross A1, the line from A1 from the plus side, so we have A1 plus. Then we cross both these lines from the minus side, so we got this 2 and this is with minus, and so on. So this is the way to represent a homotopy class and to be able to show, okay, which side of one obstacle we are going around and in which direction. So we add on top of that a tunnel constraint. Once we have the pass, this nominal pass, we can add a tunnel constraint because we don't want to move too far away from the nominal pass, and we want also to restrict the research as the search area for the motion. And in this tunnel, we can compute the pass. So here we are using very simple geometrical pass planning, which is based on cells. So all the obstacles are discretized as polygons, and then we can compute the Voronoi diagram for all the cells that comes out of the polygons. So this gives us a lot of paths. Some have the correct topology, the correct homotopy class. Some do not have. So first, what we need to do is to enumerate all the possible paths from the start to the end by just doing a depth first search. And then we take the shortest path that has the correct topology, the correct homotopy, is in the correct homotopy class. So this is in the space of the endpoint of the belt. So ideally, we would like our grippers to follow this kind of path, but first, the grippers have some volume, so it will not be able maybe to do exactly that. And second, we also have the obstacles just for the grippers, and there might be some intersection between these obstacles and the path we completed so far. But knowing this intersection will give us an idea of maybe we need to regrasp here. So then you can do the same thing in the gripper configuration space, which is basically the same but has been inflated by the radius of the gripper. So you can compute the Voronoi diagram, compute the path. So here it should be this path, like this. Here this path has no intersection with the obstacle, so we are done. But you will have some case where there is no path in the homotopy class that you want that are feasible for the grippers. And in this case, the fact that there is no path existing means that you will need to do some regrasp. And by knowing where you want it to go and where it's not possible to go, and knowing this model I showed before, we can deduce where to add regrasp. So in the regrasp case, we will put the belt through the obstacles and get the belt with the other gripper on the other side. So for the mockup I showed you, this is the kind of path we end up with. So one column means one gripper, then you have a regrasp here. Then another gripper. We need a regrasp to go back in the good direction, and we will do something else. And so I'm just showing you the most difficult part for this example, where we need to, this is the most constrained place, where we need to go between two cylinders that are very close, and the length we can use to keep straight is just enough. So here is the robotic controller playing. You have SLAM to make sure that you are keeping at the good position with respect to the mockup. We are because we have this straight, straight line hypothesis between the gripper and the cylinders. We don't need to detect the belt. So because also we are very close to all the cohesions, we are using some impedance tests or compliance tests to be able to go to the contact without breaking the rope. So still, because we are very close to the obstacle and this is still an ongoing work, the motion is a bit slow, so this is one of the future work to go fast. So with that, this is the end of my presentation. So I showed two main contributions, which are the belt shape detection and the planar belt manipulation, planar for belt manipulation. So I want to emphasize this is still a work in progress. So in particular, we need to put everything together and do the whole demo, including the transition between the different parts and the increase the execution speed. So if you have any questions, I'll be happy to answer. Thank you.
Questions? Questions? Can check online also. Questions from our colleagues online?
There are no questions online, apparently.
Okay, so here's a question. Did you manage?
Yes, yes, I have a question, please.
Yes.
I was wondering, Adrien, did you manage to handle in the SLAM the deformable object? Did you include it in the SLAM?
No, we are segmenting it out of the. We are able to know where the bobbin is and where the and to, by color segmenting it out of the SLAM so that it doesn't pollute basically the measure.
Okay, so you have two separate vision-based detection tools.
Separate detection tools. One for the holes.
Yes. But so in the final demo I show, we don't detect the shape of the bobbin. So we are running with this idea that we can have a straight part of the belt. And so we know exactly where the belt is only from the position of the gripper, basically. So we don't detect. One of the reasons could be just that we didn't have time to do everything, but a more practical reason is that the vision of the robot is not very big, and we want to use it mostly to be precise with the SLAM, so that we would need to, have a change of point of view to see the belt when we will grasp, and to go back to see a more general view for having a precise position of the robot with the SLAM. So for now, we didn't need to do that. So for the planning and execution parts, really the idea was to say we can do it without looking at the shape of the belt. Looking at the shape of the belt is important when we go out of the bobbin, because here this is something that is completely unpredictable, and we will not be able to do it without vision. The belt can fall in different way, and we need to be able to make sure that we know in which way we see it.
Okay, thank you.
Questions? Okay. Thank you so much, Adrien. Thank you so much.